Hello everybody, hello and welcome to the second session of these year continual learning seminars. And today we have the pleasure to host James Smith, who is about to talk about his recent paper titled Always Be Dreaming, a new approach for data-free class-incremental learning. So the paper has been accepted at ICCV, and we see it as an interesting topic for the continual learning community. And in fact, it's a topic which is gathering attention from many sides, and so we are here to listen to James Smith's side on his recent work. So James, please go ahead, and the stage is yours.
Sounds great. Thank you, everybody. I'm very excited to be here. Just as a forewarner, I'm very fine with being critical and open about my work, so please pause for any questions or criticisms. I think the best way that we can push this research direction forward is just being open and collaborative. So for 99% of you, you can just check your texts and Slack messages for the next 45 seconds, but I know there's at least one person listening right now who is not familiar with continual learning, so I'll just give a brief overview on that. Typical learning is visualized on the right. We have offline training with shuffled data. By shuffled, I'm meaning with respect to object classes over which we are expected to classify. It is the distribution of these object classes satisfy. Continual learning tasks are instead encountered sequentially. Shown on the right, we see that classes appear in a single task and maybe only in that task, and we must train our model to perform well on all tasks up to including the current task without revisiting prior task data. We encounter the catastrophic forgetting problem where we perform bad on prior tasks. Specifically, we overwrite information that we learned on previous tasks while learning a new task. So continual learning asks us, how do we acquire this new information without encountering catastrophic forgetting? Here is your cue to look back up again. So a classic way to mitigate forgetting, as we know, in continual learning is through internal replay. As shown in this visualization on the left, we have a continual learning agent with access to a data storage. This method, also known as Rehearsal, works very well for continual learning, but it does have some concerns. First, it requires a substantial memory budget. Second, this method, sometimes data can't be stored for privacy concerns. So instead, we want an alternative to replay. So this describes the Data-Free Class-Incremental Learning problem. The goal here is to learn some classification model from an incremental stream of tasks, but we are constrained to not store a generator trying to learn the true distribution of data or training data from the past tasks. Why would we want to do this? One, we may want to reduce our memory budget or eliminate private data storage or privacy risks. So think of some applications where this might be important. Self-driving cars generate a numerous amount of data. We can't always store all of this data for retraining because it's just so large. However, we may see new seasons through the cars or more objects appearing over years, and we don't want to simply have to store all this large amount of data and keep retraining our autonomous vehicle models every single time. Another one is social media. We cannot, or I should say we should not store private user data. User behavior, though, might change with the seasons, and we may need to be updating these models without having to store all this data. A third obvious one, healthcare. Medical data is locked down. My wife is actually a doctor here in the United States, and she goes through leaps and bounds to make sure I don't accidentally see or hear her discussing private patient data. But this data is very locked down, so how can we build useful models for this application? So I want to highlight and plug just kind of related work for people in this group who are working very hard on similar or the same problem. So first, Chesno has several works looking at like streaming Core 50 data for continual learning, including this work listed here, which introduces the methods AR1 star and CWR star. I'll pause to say that for the first time in a year, my contact has something in it. So if I'm rubbing my eye, I'm very sorry about that. I'm just going to pop it out. Okay. So Tyler Hayes, who's present here, has a lot of works looking at streaming continual learning, including this work listed here on compressed replay. Gino from Baylor has several works with bio-inspired replay methods that I really appreciate his work. And finally, there is a great review paper out there which includes analysis on coreset-free incremental learning. That's very useful. So I just want you all to know, check out all these. We are kind of different from this setting because we assume no large pre-training of the model is not a streaming task, and we aren't storing any type of generative replay for privacy protecting concerns. So I'm letting these brilliant researchers take control of this setting while I work on mine. Great. So prior work has looked at this dreaming synthetic data from a trained classification model for knowledge distillation. This might also be referred to as feed-forward inversion. The high-level idea here is that we want to invert some pre-trained model and try and recreate the training data it was originally trained on. So we start with some pre-trained, I'm going to walk you through this as a high-level overview. We start with some pre-trained classification model referred to here as T. This model is locked and not updated at all in this optimization. First, we initialize a random batch of image tensors denoted here as X. We optimize with respect to these tensors X. Second, we randomly sample some target labels from our desired class distribution, which is referred to here as Y. And our main objective is to minimize cross-entropy loss of our images X fed through this teacher T. We optimize with respect to X. Now, as you know, networks are overconfident, and we just set up this simple optimization. We may get some noisy, just very tripping-like images that are not any way close to our actual data distribution. So there's several other losses that many other works have explored in parallel to aid this optimization. So first here we have a prior image prior loss, which enforces locally smoothness. This is just L2 distance penalty and a total variance loss here. And most importantly, we actually have this loss called the batch normalization distance loss. In this loss, what we do is we take advantage of the batch normalization layers that are already stored in our pre-trained teacher. And what we try to do is have our images X match the stored mean and variances in each batch normalization per layer. And this actually works very well. So in our work, we analyze using these type of dreamed images for replay and continual learning. In our paper, you'll see we first take a few works that all work on kind of the same thing. We engineer a best possible baseline that we can make using these type of losses. And then we analyze how this baseline works in the class-incremental continual learning setting. And what we found is that these dreamed images fail when used for replay. We are not the first to find this. The paper that I'm citing here at the bottom, deep inversion, you may be familiar with. It's a paper that used this method for knowledge distillation, but in their work, they also ran some continual learning experiments. In their continual learning experiments, they found that they could do incremental learning with different data sets, that is going from data set A to data set B, but when they tried to do incremental learning within a data set, as we commonly do, for example, doing incremental sci-fi, they also found that their method just completely failed. Since that was not the main contribution of their paper, they acknowledged it and moved on. But we wanted to investigate further why this happens and see if we can fix it. So here we're first going to visualize a simple class-incremental continual learning task. On the right here, you see a TISNI visualization. This is after training task 2 of a 10-task incremental CFAR 100 continual learning benchmark. In this plot, the red vertical lines, they represent real holdout data from the first continual learning task. This is the data that we want to classify, but we have not seen since task 1. So we want to be able to remember this data. The blue horizontal lines represent the synthetic data which we dreamed from the first task. This is the data we use for replay when training task 2. The green X's here represent holdout data from the second and most recent task that our agent has seen. This is our replay. This is our the data we just trained on jointly with the synthetic data as replay. we see here is that the real data from the first task is close in the embedding space to the real data from the second task. This is a problem because this data should actually be close to the synthetic data from the first task in the feature embedding space. This indicates we have some type of feature space bias coming. Specifically, we found that when training a model on real data from the second task and synthetic data from the first task, we found that the feature embedding prioritizes domain content, that is, synthetic versus real, over prioritizing semantic content, which is task 1 versus task 2. So this is why a deep inversion or those using regular distillation strategies with the synthetic data fails. Because when we evaluate on the holdout task 1 data, we are always going to predict labels from task 2 rather than labels from task 1 because of this bias. Now, after fundamentally analyzing this issue, the question we ask is, how can we remove this bias problem? And so our work kind of turned into instead, how can we formulate a distillation strategy which does not have this bias inherent? So the goal of this approach is to move the bias problem. We see on the left of this figure that we have synthetic data from our past task with some examples there in case you were wondering what they looked like, and some real data from a current task in CFAR. We feed both of this data through our models. We have the current model we're learning, which is the lower green model from the current task. This is what's being updated. And on top of that, we have a frozen copy of our model from the end of the last task in blue. This is the model that we use for distilling information we've previously learned into our current model. Now, the key finding in our work here was that in order to do distillation with the synthetic data, we cannot have a global cross-entropy loss. Instead, this cross-entropy loss, we wanted to distinguish the semantic content between task 1 and task 2, but it's actually much easier for it to learn to distinguish real versus fake to make that to lower that loss function faster. So instead, what we have to do is do a local cross-entropy loss on the new task data using only the current task classification head. Now we found with this setup that the distillation strategy to mitigate forgetting in the feature drift is a little different than what many other methods use. So rather than doing logit-space distillation, since we're only learning our new features on the classification head, we instead have to focus our knowledge preservation in the feature space. So what we have here is an importance-weighted feature distillation loss, which tries to force the feature space of our current model to be close to the feature space of the past model with respect to the classes that we learned in the previous tasks. Finally, with these two losses, you may notice that there's no way to really distinguish between the current class task and the past task class. So we simply add a fine-tuning loss on all of the classification heads using both the synthetic data and the real data. And this loss is key to making sure that we don't have any task bias at the end. I'll also note here that there are a lot of loss functions and equations in our paper that I don't think were important to the overall story here. So if you're interested in the specific equations from the knowledge feed-forward inversion figure from a couple slides ago, or from this figure right here, please just visit our paper and you can see all of those in detail. If I try to go over each one individually, we'd be here all day, and they're not my original contributions so much, so we went with this overview instead. Now we see in our updated TISNE visualization that we have a much more ideal embedding space being learned. Here on the right, you can specifically see that the real task 1 data is clustered with the synthetic task 1 data, while the real task 2 data is clustered in separate regions in this feature space. So I'll go over some results analysis that we got with our method here. First, the details for these experiments will be in the lower left quarter of my slides. Here we have 10 task incremental CFAR 100. We have no coreset stored for replay, and we're using the ResNet 32 model, and we have all of our results are done over 3 trials. And these figure we have the mean plotted with variance in the shaded region. Thank you, Tyler Hayes. I always use your metric for forgetting. I like the omega metric. This is a metric for forgetting in which higher is better. So we show here that our method with no coreset is actually much stronger than any of the baselines that we compared to. I'd like to note that in my plots I'm showing you today, the legend is ordered with the highest performing method on the top and the lowest performing method on the bottom. So if some of these are close together and it's hard to distinguish which is which, you can just use the legend because it's sorted from highest performance to lowest performance. And our method, it performs the best in this, the second best comparison being the iCarl variant of learning without forgetting. Our main takeaway here is that we established this new state-of-the-art in the Data-Free Data-Free Class-Incremental Learning setting here. Now we also look at comparing our method to methods which do store a core set of data for replay. The details are the same on the lower left. We have 10 task incremental CFAR. There is a 2,000 image core set as done in previous works, the same models, same number of trials. We find here that our method is kind of middle of the pack in ISOC and incremental CFAR 100, with the bias correction method being the state-of-the-art that's on top. And this kind of makes sense and is still a very good result for us because we notice that our method is relatively competitive with the state-of-the-art replay-based methods which store data for replay. And we even beat just naive rehearsal and learning without forgetting with a stored core set for replay. The main takeaway here is that we are competitive with these replay-based approaches and we even exceed some of the methods. Now, I wanted to show just how each piece of our method contributes to our final performance so that you know that not just one contribution here is actually tricking you or something. So I'll first show that we do just regular class balancing with the data storage. So just removing that task balancing loss, which is very common for many class incremental learning methods, does result in a drop in performance, but it's not drastic. Now our main contribution is modified cross-entropy loss, the local cross-entropy loss. If we replace that with standard cross-entropy loss, as seen here, we have this bias problem comes back and we have a drastic effect on performance because we are trying to mostly going to predict all class labels from being the most recent task. Now, of course, forgetting is a problem. This is continual learning. So if we take away either distillation with our real data or a synthetic data in the feature space, of course, our performance will collapse greatly. I do want to notice here that it is important for us to have a distillation importance weighted feature distillation with the real data from the new task as well. And that helps preserve just the learning from the real task features that aren't present in the synthetic data. And finally, we show that if we don't have this fine-tuning cross-entropy loss, we are just always going to predict every single example to be from the most recent task because we have a giant bias here. The takeaway here is that each part of this method, both the importance weighted feature distillation loss, the local cross-entropy loss, and the fine-tuning heads, is very important for our performance of using the synthetic dream data for class incremental learning replay. Now, I wanted to give you a closer look at this feature bias from an alternative perspective. If you read the paper, this is actually what I started with. Here I'm showing you the maximum mean discrepancy distance between data distributions. This data distributions are the same ones from the TISNE visualizations that I showed earlier in the presentation. So the blue cross is the maximum mean discrepancy distance, or MMD score, between the real task 1 data and synthetic task 1 data, where the red circles is the distance between real task 1 data and real task 2 data. And for those of you who are not familiar, MMD distance can be thought of as the distance between the expectations of two feature distributions. And we show the regular distillation strategy as used in deep inversion that the distance between the real and synthetic task 1 data explodes after we start training. This is the training epochs through the when we're training the second task, and this distance just shoots up after we start training the new task. And we show with our method on the right that the MMD, after we have added our correction, is no longer synthetic task when data is mostly lower. We'll take away here is this is an alternative perspective or fundamental approach of how these distribution distances look. So you maybe has some method that so here we are the slowest at the very top. We're kind of in the middle, and then the other baselines are much faster. But the takeaway here is that we can sacrifice some efficiency.
Sorry, John, we hear you not very well, I think.
Thank you.
I don't know if it is a microphone issue or...
I think it is. My AirPods are being AirPods.
Okay, let's...
What about now?
Okay, yes. I guess now it's better. Can you talk just to confirm?
So you can hear me better now?
Yes, definitely.
Thank you. When did this occur? How far back should I go?
Not too far. I think if you start over from this slide or from the very end of the previous one, you should be fine.
Okay, and thank you for pointing that out.
Thank you.
Yeah, so just going back, and sorry about those technical difficulties, but the main takeaway here is that we have a closer look from a more formulated distance of how our the bias problem that occurs with the synthetic versus real data and how we work to mitigate that. So here you may be wondering, just how long does it take for our method to work? You don't want a method that's, sure we do improvements, but it's really slow. I talked about this image inversion problem, and you're probably wondering how long does it take? So we show on this plot that we are not the slowest. We're kind of in the middle. Yes, we are slower than just using the regular distillation deep inversion strategy, but for example, bias correction method, which is the state of the art, takes longer than us on a training time perspective. So the sacrifice to efficiency here is pretty minimal. Now, join the bandwagon. I wanted to acknowledge some other works that are going on at the same time that have similar stories and ideas to my work. So if you were at the Continual Learning Vision workshop at CVPR, you might have seen the dual teacher class-incremental learning data-free generative replay paper. They have some similar ideas to us and published at a similar time. And two newer works that have appeared on arXiv in the past 2 months are listed here. And I've looked over them, and there's some similar ideas, and I just want you to know that if you're interested in our work and you read our paper or consider citing us, please acknowledge these works as well, because the time frame was so similar. I think it's important to acknowledge everyone working on this within the same time period. Now here I want to plug a past work that I have that has a similar setting to us, and you can still hear me, right?
Yes, yes.
Okay, good. So instead of, in this data-free class-incremental learning problem setting, instead of using the synthetic or stored or generative replay work, I wanted to acknowledge another way that you can do is to instead leverage unlabeled data. So the key idea in this work we have is that we can actually use unlabeled data from some application continual learning agents environment to store as replay. It's realistic replay from the environment. And unlike some previous work, such as global distillation, which just assumes some out of distribution web crawling data to use to mitigate catastrophic forgetting, in this work here, we actually looked at the setting where this data is correlated with the continual learning tasks in the environment. Specifically, we have a semi-supervised continual learning setting where the data distributions actually reflect the object-object correlations between labeled and unlabeled task data. And we found that actually these correlations can really poorly affect some methods out there, such as global distillation. So if you're interested in semi-supervised continual learning, take a look at our work and notice that the distributions that can actually occur in this kind of setting can actually have a profound impact on the method. Yeah, so lastly, I wanted to just kind of acknowledge some shortcomings in my work as people start working on this type of setting, kind of give you some of my thoughts so that maybe you can improve upon my work. So there's actually still a giant performance gap that needs to be closed. So when I did some ImageNet experiments, you can see here that actually I don't even beat LWF from iCarl. So one big reason this happens is actually the model inversion for complex data sets right now is still very weak. At the time I actually did this work, there was one work that could successfully do it for ImageNet, and it required one generator trained per ImageNet class. So for ImageNet 100, that would require 100 generators, or for ImageNet 1,000 generators. Obviously, I do not have that kind of scalar computational resources, and that shouldn't be necessary for continual learning. So there's this orthogonal problem that if you can improve and scale up the model inversion for these more complex tasks, then you can equally see some contribution gains in this incremental learning scenario and setting. Second, I think there's a deeper question here that I kind of circumvented. In our work, what we did is we diagnosed and acknowledged this distribution mismatch happening when using the synthetic dream data for replay and incremental learning. And what I did to mitigate that was redesign the distillation and loss functions. What I think could actually be analyzed and looked at deeper is this problem of how to do distillation with these two shifts in data. So there's two shifts between the replay data and the current task data. This first shift is the semantic shift between task 1 and task 2. And the second shift is the real versus fake shift here. And yeah, I think there's this deeper question that could be explored with like a domain adaptation perspective that could really find much better performance here. So please do better than me. I think there's a lot of ground to gain here. So I just wanted to acknowledge that and give some of my thoughts in case you were interested in looking at this work yourself. So yeah, I'd like to just thank the collaborators that we have. You can follow this link to see our project page. You can check out our archive by using the QR code. I will say that some people have asked me on this. The code is going to be pushed before the ICCV conference begins to my GitHub page, possibly this weekend or possibly today, hopefully this weekend. Did my voice go out again?
No, we can hear you.
Okay, sorry. I've started doing this thing with AirPods on a Windows machine. Sometimes it's not as good as the AirPods with my Mac, and they've gone out twice during this presentation. So my apologies.
Many conflicts, but we heard you fine for most of the talk. So.
Okay. And then just if you want to connect, please find my email from my archive page or message me in the ContinualAI Slack. I would love to chat about this kind of work or just connect and talk. And that's all I have, so thank you very much, and yes, discussion time.
Great. Thank you very much, James. This was a very nice talk, also clear, and I think it definitely open up a new, well, if not new, at least an interesting research direction for continual learning. So the list of papers you mentioned, it's quite impressive for the very short time in which they appeared on similar topics. So it's good to see the interest of the community towards this project. Maybe also because, as you were saying in the beginning, there are lots of practical applications that would benefit from such a setting in which you don't need to replay lots of private, sensitive data to be able to mitigate forgetting. So even achieving state-of-the-art or good performances in current benchmarks, it's very important to establish the importance of the approach. So thank you very much for these insights. So let's look at the chat. I think that also people are watching us in streaming can see the chat, so it's good. I can start with one question. Of course,
okay.
Everybody feel free to unmute if you can, or raise your hand, or write in the chat, or in the streaming on YouTube. I'm monitoring in some way also these displays. So as for one question that came to my mind, looking at the model, the architecture you used in your experiments, I was wondering how it is, how much difficult it is to generate this synthetic data. So what are the assumptions that you have to make for the model? So like you mentioned batch normalization, so you can exploit statistics, for example, to generate synthetic data. How much this depends on the underlying architecture, or it can be instead generalized to different kind of models?
Yeah, that's a great question. So I only explored this with ResNet variants, several ResNet variants, the only ResNet variants, and having these batch normalization layers is very important and crucial to this. But besides that, we did no special training during the task. Like, we trained the very first task in a very standard way as done in every other continual learning paper with ResNet. So we made no additional assumptions beyond the normal ones. But I think there is a great question there on, one, can you do something to train it to make it actually better? And then two, how would this work with other types of models or other types of statistics stored in there? And I would suspect that my method could be more generalized to other types of inversions, because it's not, our approach is not reliant on the way we produce our synthetic data, but I have not actually specifically explored that. So maybe we could look at other inversions that don't have these batch normalization layers, even generative replay, as we know that you need like for true generative replay, you need state-of-the-art high-performing GANs to actually get reasonable success. And if you don't have those very good image quality, then it's going to collapse. Perhaps my method with deep generative replay would also solve that issue. I have not explored that either.
Yeah, I mean, this is something that, of course, it's necessary, and in computer vision, it's also much easier to have these general statistics about the data. So I always look at the problems with the lens of sequential data processing tasks, since this is let's say my research topic. And when you move to sequences, it's much difficult to generate the data. Yeah. So I think that this could be a very interesting research direction. A very challenging one, I would say, a very challenging one, but a very interesting one.
And the same with that, you'd have to make some assumptions, like always have the very same sampling size, I guess, or number of samples. You'd have to make some very strict assumptions on it to make it even reasonably work.
Yeah, I agree on that. So I see a question on the chat. Tokir Hamad, I hope to pronounce well the name, asks, what do you think was the reason that approach did not do good on ImageNet 100?
Yeah, and that's a great question. I briefly touched on it, but I'll expand some more. I can get there. Yeah. So our contribution in this paper was not the feed-forward model inversions. Other works have already worked on that. Our contribution was with respect to how can we use these for distillation and incremental learning. And these feed-forward inversions have yet to scale, at the time this work was done, I should say, have not scaled up good to images like ImageNet. So the reason it didn't work is because there's, out of the box, our method cannot create or recreate good images for ImageNet to use for distillation. I mentioned an example. At the time this paper was submitted and done, there was one work that had good quality on ImageNet, but they had to store one generator per ImageNet class. So if we wanted to do ImageNet 100, we would have to have 100 generators all working together to invert the ResNet model, which is just, even if I did have the computational resources for that, that's just not feasible for continual learning applications in which we're trying to constrain ourselves for efficiency. So that's a kind of an orthogonal direction, I would say. As soon as we can improve these image inversions for the more complex images, which has sometimes been done, then this will be much better. Do you have some samples to check the quality of generated images? In this presentation, what I have a few in my model slide. I went too far. Right here, you can at least see a few in the top left. There's some images of cars. If you want to look more, just go look at the Deep Dream original paper, which is cited in my work. And the papers that are focused more on this have just much more examples, because that's what their paper is about. So you can just see pages of images that they created with their methods.
Yes, I would also add that while it would be nice to have sharp, synthesized data, maybe it's not even necessary to reach that point. I mean, it really depends on the objective
right.
for which these data are used. So yes, even blurred images could be even fine for the job.
Right, that's kind of the alternative view of this work, is if you have imperfect replay data with these two shifts, how do you perform incremental learning?
Yeah.
Because you still have valuable information, semantic content in those imperfect images that can help you mitigate forgetting, but you can't just use the out-of-the-box distillation strategies to achieve that.
Yes, and as you said, I mean, if someone comes up with a new, more efficient way of generating these images, your approach allows to immediately put the new discovery in place and see an improved performance, hopefully. So yes, I also see this as two connected but orthogonal problems, as you said. So I don't see any other questions. Last chance, people, to ask your question if you have further doubts, curiosity. I guess not. So let me thank you again, James, for the awesome presentation. And please remind that this is also a YouTube live stream, so you can check out the video also in a few hours, I guess. And yeah, thank you, James, and see you all at the next continual learning seminars from ContinualAI. Thank you very much.
Thank you, everybody, for coming.